Yeah, so this is going to be quite a different talk. I'll be talking about rocks, but more from a geophysical perspective. So looking at multi-scale approaches for estimating cover thickness. So first on the camp scale, so if you want to drill a hole, how much cover do you have to drill? So predicting that cover thickness. And then later on looking at the basin scale, regional scale cover thickness estimation. A lot of the work I'm talking about is from my co-authors, mainly from Geoscience Australia. I'd just like to acknowledge their input. Okay, so the outline is, so Geoscience Australia's task of the Stavely Project, or one of their tasks was to estimate the cover thickness prior to drilling, prior to the stratigraphic drilling. And we used a number of geophysical techniques. I'll talk about 3 of them. So the first one's using pre-existing airborne magnetic data, using a target magnetic inversion modelling technique. And then we collected refraction and passive seismic, so we'll talk about the results. And then after that, we'll talk about the more regional look, cover thickness. So Murray Basin, looking at some benchmarking at a few different magnetic depth estimation methods, see which ones work, which ones don't. Then machine learning to basically connect the dots between your depth estimates, produce a cover thickness surface, and then looking at that surface in 3D with some solid geology maps as well. Okay, so estimating cover thickness. So reduce the risk to the driller. So you don't want to blow your whole budget drilling through kilometres thick cover, which you didn't think was going to be there. So reduce the risk to the drilling. But also we wanted to investigate a range of exploration techniques to provide a toolkit for the explorer. And with the understanding that some techniques might work in some areas, but that same technique mightn't work in different geological terrains because of the properties of those rocks. So I've got a magnetic image of the Stavely Project area, and the numbers are your drill holes, the proposed drill holes, at this stage at least anyway, because we're going in before the drilling. And most of the drill holes are up in the north, sitting within the Murray Basin cover region. So you've got Murray Basin cover into your basement. But this hole 1 down here, it's a bit more problematic. You've got the newer volcanics, which is this stippled magnetic signature, before going through Otway sediments and then into basement. And hole number 2, you've got Grampian group cover before going into the basement. Okay, so looking at the physical properties of the various cover basement units. So basically you want a large physical property contrast for any of these methods to work. So if you look at the Murray Basin, if you're looking at magnetics or the density, magnetic stability, density, P wave, S wave velocities, and they're all low, which is great because the basement is generally high. From a magnetic modelling point of view, you want to have magnetic anomalies in your basement. The newer volcanics is problematic in that it's very strongly magnetic, which tends to just sort of blow away your basement magnetic anomalies. It's also moderately high density and velocity as well. So there may not be a good property contrast. And some of these other cover sequences may or may not work. Otway, Grampian's non-magnetic is great, but the velocity and it might not be a high contrast to your seismic passive methods, but we'll see. So starting off with the magnetic depth estimation methods. So this is an image of the flight line spacing of the airborne magnetic data, and the Stavely Project area is covered by very good 250 or less flight line spacing, which is just ideal for magnetic modelling methods. So the method we're using is basically targeted magnetic inversion modelling, or TMIM for short. So there's a magnetic image at site 4, got these northwest trending magnetic features. And the idea is and these are the flight line data. So we're working with airborne flight line data. So the idea is to target clean looking anomalies in the vicinity of the drill site. And then simulate the geology by dipping tabular magnetic body, and then running inversion on that. And it's a parametric inversion, and so the inversion is basically modifying these properties to minimise the misfit between your observed and your modelled magnetic data. And one of the properties, of course, is the depth, which is what we're primarily interested in. And looking at the results. So the black dots are your cover thickness from the drilling. So the drilling's now been done, so we can test how well these methods have worked. And generally it's done pretty good results. So the green dots are the estimate, and I've got some uncertainty associated with each magnetic depth estimate. And yeah, majority of them pick them within error. A couple are overestimated the cover thickness, which is, from a drilling point of view, maybe that's a good thing. It's better to have a pleasant surprise rather than an unpleasant surprise. And looking at a couple of sites where the method worked, and you can see why the method worked. So this is the stratigraphic sequence. So you've got your cover, you've got your basement, and the wiggly line is your magnetic susceptibility from wildline logging on the holes. And both sites, there's a good kick at the top of the basement, kick in magnetic susceptibility, and that's what you're picking up with your magnetic modelling. So that's all very good. Couple of sites where I couldn't get any depth estimates. So site 1, we've got the newer volcanics, very strongly magnetic, non-magnetic Otways, and then there's no discernible jump when you start go into the basement. So there's no magnetic anomalies to model. And site 14, sort of similar story. There's a bit of a magnetic response from the lower basin sediments, but there's no real jump when you get into the basement, so it wasn't possible to produce a depth estimate at those sites. But generally, hey, it's done a pretty good job. So moving on to the refraction seismic. So we went down, a group of us, 48 geophones set up in an array, 240 metres long, and our seismic source was a sledgehammer. We've now sort of upped the power. We've got a accelerated weight drop, but at that time, that's what we had. And we weren't very confident. We didn't think we'd be able to image cover thickness, say, beyond maybe 20, 30, 40, 50 metres, that sort of range. But we were pleasantly surprised. So we did shots within the spreads, at the end of the spreads, and also off-end shots up to about 1 kilometre off the end of the array. And this is a result of one of the shots. So this is your spread here for your geophones, the location of the shot right on the edge of the spread. And you can see the first breaks. And looking at another shot a bit further out on the end of the line, and I've now drawn in the refractors. So we've got two fairly lowish velocity refractors. They're from interfaces within the sedimentary sequence. This is within Site 7, within the Murray Basin. And you've got a higher velocity refractor, which is reasonable basement rock velocity. So that's your top of basement just there. And from this information, you can model your cover thickness, which is what we did. And again, it's done a pretty good result. We managed to get depth estimates to close to 150 metres, which is great. Generally within error of the drilling. A few of the sites, we just didn't have the source. Site 2, there wasn't the contrast between the fairly high velocity Grampian cover with the basement, so that was a fail, I suppose. But at least we can get minimum depth estimates at, say, this site. Site which worked, and you can see why. So you got your cover, you got your basement. This case, this is a density profile from the wildline logging, and which you can use as a proxy for seismic velocity. And you can see top of basement, there's a major jump, and that's what you're picking up with your refraction result. So that's good. Site 1, refraction's never going to work, and that's because you basically got the high velocity newer volcanics over lower velocity sediments beneath it, which creates an inversion layer, and refraction is just not what you want to use to go into this environment. And okay, this one overestimated the cover thickness, but we've got a reason for it. So if you look at the density profile, you see that there's basically there's not a big jump at the cover basement interface, but then it creeps up as you go down. And if you look at the hyperspectral results from the drill core, work done by Matilda Thomas, there's basically elevated kaolin counts at the top of the hole, which sort of reduce as you go down. And kaolin's an indicator of weathering, so essentially at this case, at this hole, the depth estimate is from the top of your fresh basement, basically your weathering zone. So generally refraction's done pretty good. Okay, passive seismic. So two methods. There's a H-on-V method, which uses just a single receiver. It's very quick, which is good. SPAC method, where you set out a series array, in this case a spiral array. And what you're using is far-field seismic disturbances from earthquakes or cultural noise, etc., creating a ground roll which then sort of propagates across your spread. H-on-V method, said it's very quick and dirty, but it's also depth limited to maybe 150 metres or so. The SPAC method, in theory, it shouldn't be depth limited. You just sort of step out your array to get to image deeper. Okay, and going on to the results. Also very good. Most of the sites picked basement within error. We were very new to the game, I suppose. A couple of sites we had data problems, and so we couldn't get results for site 10 and 11. But generally fairly good. And looking at some of the inversion results. So you're running an inversion on, in this case, the H-on-V, the SPAC, and you can also run a joint inversion as well, which can tighten up the results. So the black line is I suppose, the best model inversion, and the grey is when you're within 10% chi-squared. But it basically gives you a feeling of the uncertainty within inversion. So if you look at the H-on-V, then uncertainty is a lot lower than the SPAC, and then when you run the inversions together, the uncertainty is lower still. So that's all good. Now, where this method really excelled was where you had this problematic site with the high velocity newer volcanics over the top of the Otway, over the top of the basement, and it just nailed the result. It was fantastic. Uncertainty's a bit bigger, but hey, that's pretty good. So, conclusions. So that TMIM estimation method basically worked better than expected. I've been sort of doing depth estimation using various magnetic methods in the past, and I know there's a lot of uncertainty, but I think using this approach where you're targeting magnetic anomalies around sites, doing a weighted average to get your depth, it works. Fails when there's nothing magnetic in the basement, or you have a very strong magnetic cover. But also the big bonus is the data's free and it can be downloaded from database across the whole country. The refraction seismic also produced good results. We were surprised that the seismic source, our sledgehammer, could image 150 metres or so into your cover. But now that we have a stronger source as well, we can image deeper. Which we've been doing. So we're doing a similar program for the Thompson Collaborative Project, what we've got going as well in the Thompson region, and also we will be doing another one in the Tyser region, which is up in the Northern Territory, Mount Isa, Tennant Creek, Mount Isa region. So that's the next drilling program which is going to be happening. But you can acquire 2 sites in one day, but as I mentioned, can be depth limited depending on your seismic source. And passive seismic, also very good as well. It nailed that problematic site, the only method which managed to do that. H&V methods, super quick, probably cheap, you're only using a single seismometer, depth limited, but even the SPAC method, they're cranking out 2 sites per day as well. And this has all been written up in a report, which is on the GA website. Okay, so moving on to this benchmarking. So now we're looking at a larger region, say basin scale, cover thickness estimation. And again, I'm showing this image again, basically the flight line spacing across Australia, just to highlight that, you know, Australia has the best coverage of magnetic data in the world. And all those warm colours, you can produce reliable magnetic depth estimates if your geology is suitable. So you look at the magnetic image of the whole continent, and you know, this is basically, you can sort of think of it as a pseudo 3D image. So there's a massive amount of depth information in there, millions and millions of anomalies. You've just got to try to extract that information out. Okay, so benchmarking. So there's numerous magnetic depth estimation methods out there. So the question was, you know, which one to use? You know, we're going to be doing this across the whole country. So what's the easiest and the most reliable methods? This is a magnetic Euler deconvolution. It's been around for many, many years. It's a grid-based method, so basically you feed in a grid, and it's very good at producing lots and lots of depth solutions. But Murray Basin has also got reliable drilling, and so we can compare the results of these various methods to the drilling, and this is what you're seeing over here. So this is a scatter plot showing your drill depth, gives you depth estimates, and you can see it's scattered everywhere. Ideally, it should be lying on the green line, but it's not, and you look at the correlation coefficient, which is very, very low. So this sort of method, although it's quick, I don't think it's particularly reliable. Tilt depth is, I suppose, similar. Again, it's a grid-based, it works totally different way of actually generating depth estimates. Runs on grids, it's also very quick, but I think it's producing fairly similar results in that there's just a massive scatter with very low reliability, and so we're sort of not going to be using this. Another method, so this is now looking at profile data, so going to the flight line database and working, doing modelling on that. It's more time consuming. This is a annuity depth estimation method. This is done by Mark McLean, but the results are orders of magnitude better than those grid-based methods. And you see R squared of 0.42. So, hey, we're right on the right track, and that's great. Now, because we had such success in the Stavely, the pre-drilling geophysics, we decided to crank the TMIM method out across the whole Murray Basin to see how it goes against drilling, and it did pretty good. So, correlation R squared 0.68, which is a lot better. So this is the method that we're going to be using now for cover thickness estimation. I suppose the drawback is it's quite time consuming to generate a magnetic depth estimate, but hey, it's reliable. Okay, so now you've got all your depth data, whether it's drill holes, magnetic depth estimates, whatever, seismic. You want to create a surface out of it. Traditionally, you would do some sort of gridding method, kriging or inverse distance, minimum curvature, whatever, to basically interpolate between your control points. But within GA, we've been using, I suppose, a new approach, a data mining, machine learning approach, which is work that John Wilford and Sadipka Baska has been doing. And so essentially what you're using, so basically your points now become a training set. So you're looking at the relationship of that training data with respect to gridded data sets. And then, you're using that relationship to predict what's happening between your training points, your depth points. Rather than just interpolation, you're now going into sort of predictive space. So this has been trialled in the Murray Basin, so the first region that we trialled this at GA. This is just highlighting the all the drill hole data that's gone into the model, and which incorporate, as part of that training data. So we use the magnetic depth estimates, reflection, seismic, etc. So that's your training data, and what you're trying to train up are these other grid images. So topographic relief, surface geology, distance from outcrop, surface geology, Cenozoic geology, various filtered grids, gravity, TMI. And the idea is that all these grids have some sort of depth information within it, but this whole machine learning process will tease out what that information is and then predict what's happening between the actual your control points, between your drilling in this case. And this is one of those models. So this is your Cenozoic thickness of the Murray Basin. It's a basin-shaped, I suppose, saucer-shaped basin, up to 650 metres deep. And you can compare the result of your model against all that training data as well. And it's a bit of scatter, but look at the correlation coefficient 0.8. That's a very good fit as well. Okay, now you can run multiple models. So the idea is that you can just take a subset of your training data, randomly selected, rerun the models multiple times, and so then you start get a statistical analysis. So then basically your base surface is, I suppose, your best guess of your cover thickness, but you can also get a feel for the uncertainty as well, so you can start applying upper and lower bounds to what that cover thickness might be. And so this is a 3D image of that Cenozoic thickness surface. It's in EarthSci, a 3D mapping or 3D visualisation program that I've been using in GA. I've actually been developing it. Malcolm Nichols been leading that process. There's a massive vertical exaggeration. So these are the snowy mountains up here, and you're down to about 650 metres cover thickness in the centre of the basin. And this is available on the GA's website for download. Okay, so you now know what your cover thickness is. You want to know what's underneath your cover. And so in GA, we're doing this process of generating solid geology maps. So this isn't a solid geology, so this is your surface geology. Basically showing all these yellow polygons here are your Cenozoic cover. And this map here is now having the Cenozoic stripped off it. So pre-Cenozoic geology of the region. This is done by Songfa Lu. It's quite recently released. It's also on the GA website as well. So now you can track your prospective geology up underneath your Murray Basin cover sequences. And this is my final slide, and it's just a 3D drape of that pre-Cenozoic geology over the top of the Cenozoic cover thickness. So now you've got that geology sitting in 3D space where it should sit. And yeah, I'll leave it there.